Thank you for that introduction. I'll try to keep it a little shorter so that we can wrap up on time. So, as he said, my name's Kyle Reinholt. I'm from the University of Colorado Boulder, and I'm here to present my work EyeDescribe on behalf of my co-authors and colleagues, Darren Guinness and Shaun Kane. And this work involves creating accessible touchscreen artwork, utilizing behavior of sighted people. So someone who's blind that's browsing the web needs to have access to the content that's within the page. This is most commonly represented using a text description. When a blind person encounters this image, the computer would say, "Storm below Mount Fuji" from the series 36 Views of Mount Fuji. This description doesn't tell us much about what is actually in the image. However, somebody who is going to describe this image might start by talking about the giant wave that's looming over the tiny mountain in the background. And already we have more information about what's actually in the image and where the objects are. And this is the type of information that we want to capture. When a content author puts an image into their website, it's up to them to provide a description for that image. If they do not provide a description, then it's as if the image is not even there. So the content author is responsible for manually submitting a description along with that image. However, people don't want to put in the effort to provide a thorough description. And so to lighten the load, we use automated approaches such as artificial intelligence, like Microsoft Caption Bot or Google's Vision API, to provide descriptions of images automatically. Here, Caption Bot thinks that this is a close-up of a logo, and Google Vision API thinks that this is a shoe and a hat. And Google Vision is 90% confident that there's a shoe in this image. And though this approach could lighten the workload, the accuracy of these systems with artwork is still not, the accuracy is just not there yet. And so to bridge the gap between these automated and manual approaches, we came up with the idea of use-driven accessibility. This is a concept where we can create accessible artifacts from interactions with an artifact without requiring any conscious effort or work. So imagine that you're at an art exhibit with your friends and you're looking at an image and discussing it. There's a lot of information that's going on during this transaction. And so if we could embed sensors in this image, such as eye trackers and microphones, we could record some of that data that's happening in this transaction and then use this data for later consumption. This approach would give us additional details about the image, and we can also embed this hardware inexpensively. And so the idea is to collect data from a sighted person looking at an image while talking out loud. And we know from previous work that when somebody describes something, that they look at it and they fixate on it. And so this is an example from our work that displays the same thing happening. The timestamps from the description are highly associated with the timestamps from the gaze. And so our system, EyeDescribe, takes three things as input, which is eye gaze, an image, and a description. And this can be queried and aggregated in ways that we can output a touch-accessible image, where someone who's blind or visually impaired can physically scrub over the image and hear descriptions of the objects within it, using this speech and gaze data. And so we created this interface to answer two big questions. We wanted to know if using eye gaze and speech data could create representations or useful data. And we also wanted to know if we made this interactive, if people would understand where things were in the image. And so initially for the system to work, we had to collect gaze and speech data associated with images. So we did a study where we had 6 people come in and describe 12 different images. We recorded the data using an eye tracker and a microphone. So the eye tracker would yield an XY coordinate and a timestamp, and the descriptions that we recorded with a microphone were transcribed using IBM's speech-to-text API, which would yield a string and a timestamp. And so this acted as the input for the EyeDescribe features, and then users could access that data using 4 different features. So a person who's blind or visually impaired might want a detailed description of an image. So the first feature allows a user to be read a description, a detailed description of the image, where the second feature, the user may not want to hear a bunch of detailed information, and so this will allow them to get a quick overview of the image. And this feature lists the most frequently used words associated with that image. And then there's a third feature where the user can explore the image by scanning around. And then there's also the search feature where the user can query the system for the location of an object. And now I'll show you examples of each of these features.
Animals are posing.
So the user can perform a single tap to hear a detailed description.
Inside of a barn. There is dog in the center. A cow on the right. On the other side, there is a chicken towards the front with a sheep directly behind it.
The user can double tap the image to get a list of the common objects.
Objects in image. Dog. Sheep. Ram. Chicken.
And the user can explore by touching and dragging their finger around.
Goat. Located boards. Located horse. Located sheep.
And the user can say the name of the object, and the system will verbally guide them to its location. So in this video, the user performs a 2-finger tap, and then the system, using directions such as left, up, right, or down, will guide the user until it reaches the location of the object, where you can query such as saying, where's the dog or the cow or something along those lines. So these were the 4 features in the interface, and using it, we conducted a study where we wanted to know if blind people using it would be able to tell where things were in the image. So we had 7 blind participants. There were 3 phases. There were 11 images, and the study lasted approximately 90 minutes. Here's just an example of some of the images that we used. They were from 3 categories, such as landscapes, still lifes, and portraits. And in the top row is just some examples of objects that we could tag using gaze and speech. And so this study consisted of 3 different tasks. The training phase was used so that people could understand the features and gestures in the interface. And then we performed a second task where there were 3 images and participants could explore them for as much time as they'd like. And they performed a think aloud so that we could assess their reactions in real time. And then it would also allow them to further familiarize themselves with the interface. And then for the third task, we would give the participant the interface, and they'd have 5 minutes to interact with an image in both conditions that I'll talk about in a second. Then we would take the interface away and ask them to place the location of an object. Then we measured the distance between the placed object and the actual object in inches. And after all 3 tasks, we conducted a semi-structured interview to further assess. And so, in comparing location accuracy, the data shows that people were able to better recall the locations of objects using the spatial features where they could physically touch the screen versus the non-spatial features where the system would just read them a description. So we performed a one-way repeated measures ANOVA, and this found that there was no significance between the spatial and non-spatial conditions. But what this says is that the images created by our system were able to be understood at a similar level as having a thorough description of the image. And so also the information that we received during our study showed that there was an overall positive feedback about the system. For example, P1 said it allowed me to get a mental image drawn in my brain. It's like the spatial features allowed the user to draw a picture of the image in their head because they could feel where things were located in relation to one another. P1 also said, I like the ability to explore and look for things. And viewing images for the participant became more of an active experience rather than a passive one. And P3 said the worst was when there was no explore mode and just going off of people's descriptions. And this participant liked the ability to explore and discover things for themselves. So this assessment, or this feedback, showed that people enjoyed exploring artwork on a touch screen. And so to further improve this interface, EyeDescribe could be extended to adapt descriptions based on a gazer's behavior. Meaning if these images were displayed on a digital screen, as somebody is looking at the image, it could zoom into certain areas or crop areas, and maybe the image could actually query the gazer to explain more about certain features. And so then on the user side, the user could query the system for the gazer's behavior, such as what did people look at the most, or what did people look at first, or what did people not really look at all. And then also providing the ability to dial into different layers of the description or data, such as colors and textures, and even subjective feedback. And so in this work, we explored creating accessible images for people that were blind or visually impaired using sighted people's data. And we believe that understanding how people engage with a piece of art can provide unique insights into how to make that art more accessible for everyone. And I just wanted to mention that for this talk, I extracted a very high-level view. We had to perform a feasibility study and another user study that we discussed in great detail in the paper that I did not talk about today. So please read the paper. And that's all I have for you today, and I'm open to any questions.
So thanks a lot, Kyle, for this interesting and short talk. Great. Are there any questions to Kyle? Yes, please. Just repeat your name so that we get even more familiar with it.
Hello. So I'm Laurent Thévin from LMU Munich. Actually, as I work with people with visual impairment, I have a lot of questions. So I just, maybe we'll talk later for the next one. But the first one is for when we, in our previous work, the really strong requirement for people with visual impairment was to be able to use two hands so they can have one reference point and make the difference between 2 points to have like absolute and relative positioning. And so do they explain some of the result, and did you have this feedback?
Could you repeat the question in a different way? Are you saying that that people might use their hand to reference a location, and that might influence the results in one way or another, or?
Yeah, so there are actually two questions in one. The first one is, do you add such feedback from the user, the users of your study, the blind person? And do you think it may have like changed the result regarding positioning or relative positioning of elements?
So, I'm sorry, I don't understand the question. I don't know if it's because I can't hear you very well. So I'd definitely like to discuss this offline if you stick around after this. I apologize for not having a good response for you up here.
Yeah, sorry, just do it later. While you're still thinking, just a short question, a technical question. So you recorded eye gaze, I understood, and I noticed that you always have rectangular bounding boxes. So of course you are only looking at the fixations, I assume. So did you also consider to have a better estimation of the extent of an object? For example, adding some computer vision method, just to have an initial seed point, like I'm looking on the sheep, and of course the computer vision algorithm might be able to to determine the boundaries of the sheep better, because in cases also in your example image where you have a lot of overlap or maybe cascaded objects in the scene, this might be very beneficial to see the difference.
Mm-hmm. Yeah, I really like that suggestion, and for future directions, I think that would be a great place to take this work. So this was just early developments in creating a spatial map for images, and just so that people could get the relative spatial information from the image to build a mental model of where things were. But to that, also we analyzed the gaze using 4 different metrics, where we looked at raw gaze accuracy. So if somebody said dog, we would look at how many gaze points fell within the bounding box, and then divide it by the total number. And then we also looked at fixations, like you said. And then we did raw kernel density estimation, where we did a kernel density on raw gaze points, and then also did the density on fixation points. And but to find the edges of the actual objects, we did not use any computer vision.
Yeah, all right. Good. Okay. I have the last, or you have a question? No. Okay. A last short question. Do you think it's always helpful to let blind people look into our brains? In other words, do our descriptions of sighted people really help them? Or maybe, since they have a different mental model of exploring the world, a different representation could be more beneficial?
So yeah, there's a lot of representations that are more beneficial, but when it comes to exploring images on the web, a lot of people don't put the effort in to even describe images. So this is just a way to extract more data, as much data as we can, from people just interacting with things to create a more accessible internet, especially in the context of artwork, because most of the time, and if you go and look on digital collections of artwork, such as like the Metropolitan Museum of Art, a lot of the times you'll see that the descriptions are intended for sighted people, and they assume that the user is sighted, and it will talk about the historical details of an image rather than where objects are located and things like that.
Mm-hmm. Right, so let's thank Carl again. If there's no more questions. And also, sorry, I forgot that. Of course, let's also thank Shota Kazuya.